remember, was putting electrons in their homes. We're going to do the same thing. Now, let me start off by, if you wanted to give yourself a heading on this, you could give yourself a heading of electron configurations could be your overall heading if you want to do that.
Oh, so we're taking it?
You are going to take some notes on the side as we're going on, but particularly here's our goal. Would you agree with me that atoms always want to have their electrons as close to the nucleus as possible?
Yeah. Yes.
Isn't that the guiding principle? And when we looked at it with Niels Bohr, it was pretty straightforward. He said, there's 7 energy orbits. Electrons want to be in the first if they can be. And if the first is full, you go to the second. The second is full, you go to the third, right? But we now know that the orbit idea doesn't work. But the orbital idea does work. Same principle, though. So we're going to be following something called, don't have to write this down. I want you to just kind of absorb, kind of watch what I'm doing. When I start writing out stuff, that's when you're going to want to really focus in. Almost everything else that I have said is in your notes. So that allows you to, hopefully, to pay a little bit closer attention. Yes, ma'am. You're going to need some space where you can write out the notations I'm doing. But it might, I would suggest having a separate sheet of paper outside of that you can do some work on. Okay. Yes.
Where in the packet?
So we're starting with quantum numbers, right after quantum numbers, where you go to electron configurations. It's going to be towards the end. Any other questions?
Here? Quantum numbers?
Right after quantum number. It starts with electron configurations where you're going to go. Now, but more importantly, the reason I'm giving you my master notes is that I want you to just kind of listen and follow along with what I'm doing and see if it makes sense. And if it does, then you're going to be in good shape. So, can I start with a prayer for all of us here? Because some of us, man, I just feel tired. Do you guys? Yeah. A little bit weary, a little bit headachy, a little bit sick. We have people are getting concussion-y and stuff. Taylor, you're way back there by yourself. I feel kind of sad for you. Do you want to come any closer or no? Really? That is a good response. All right. Permission granted. Let's pray. God, I'm grateful for these students. I feel incredibly privileged to teach them. I'm grateful that when we are not feeling great, we have a place to turn, and you'll always be there for us. So I pray right now specifically for those of us who are just either dealing with health issues or we're just weary, that you give us strength. I pray this class would be good, that I teach clearly, and that the students would learn. In Jesus' name, amen. Okay, so here's the idea. We're going to put electrons in their homes. We're kind of like the electron placement division, right? So we're going to take an imaginary number of electrons, and we're going to try and put them into orbitals. And the only guiding rule that we have is simply this. Let's put electrons in the lowest energy orbitals that are open. If an orbital fills up, we're going to go to the next highest orbital that is open. Are you with me? We call that putting electrons in the ground state. Now, if you take a look on the board here, I have drawn a recreation of the 7 energy levels in the atom. Now, we talked about this briefly last class period. We said that there's 4 main types of orbitals that we deal with: S, P, D, and F. Agree? And those orbitals come in sets. S orbitals come in a set of 1, P orbitals come in a set of 3, D orbitals come in a set of 5, and F orbitals come in a set of 7. And that's important because if I look at the first energy level, let's just pretend that, see these numbers go 1, 2, 3, 4, 5, 6, 7, right? Do you see at the first energy level, isn't there only an S orbital that's allowed here, right? But at the second energy level, can I have an S and also a set of P's? What's important about that is that an S orbital is 1 orbital. It comes in a set of 1. P orbitals come in a set of 3. So we have to acknowledge that altogether in this row, we have 4 orbitals, not just 2. That 2 in front of the P represents the energy level that a set of P orbitals is in. It does not tell us that we have 2 P orbitals. Does that make sense? Similarly, if we look at the third energy level, don't we have a 3s orbital, then a set of 3 P orbitals, and then a set of 3 D orbitals? Now, again, 3 D orbitals means 5 orbitals at the third energy level. Now, we're going to play a little game. It's super fun, but not really. I don't know if I should pause this or what, because I don't think I can pause it. Yeah, we're going to play a game. So here's the game, and whoever's watching this later on can, I think Annabelle is not here. Let's see. So you can see what we're going to do. All right, so here's what we're going to do. We're going to play the game called How Many Are There in a Set? And it's going to play like this. in front of you, you're going to hold up the number of orbitals when I say the shape of the orbital. So if I say S, in front of you, you're going to go like this. If I say P, this. D, and F. The winner gets a prize. Okay, so I have to be able to see all of you. So why don't we kind of like stand up around the outside edge, kind of in a semicircle. And as soon as you're knocked out, you are going to come be part of the group that picks out other people. Okay, don't go far away from me. So all I'm gonna do, I'll just do a practice run with you here. All we're gonna do is this. I'm gonna go S, and you go what? D.
3, 5.
Oh, wait, that's 7.
D 5. P. And F. Right? So let's do a slow run on this. Now, when we actually do it for competition style, if you guys are like 5, we do that, it doesn't work, right? So let's go. Ready? P. B. S. P. S. P. F. S. D. P. Got the hang of it? It's a little bit tricky when we do this. So, by the way, this is super silly. I do understand this. But it is really important that whenever we think of, hey, I'm dealing with p orbitals, you think 3. Or d orbitals instead of 5, because that's going to help us with our orientation. All right, so this is live. Rat out the people around you if they don't do it. I'm going to try and catch you, but if you do any hesitation, you're gone. And then you come join me over here, and we'll try and find other people. All right, please stand up. This is a standing. All right, here we go. Ready? I can't see you, so you're going to be moving over here. All right, let's go. P. S. D. P. Come up here to the front and help me out with you did like a weird like.
I was like.
So you're watching right now. You're gonna help me out. You're watching people that do any hesitation. Let's kind of scoot you guys together that way. All right, we're watching. Can you keep an eye close to the side?
Yes.
Right, here we go. D. Gone. You're gonna help up. You're gonna help me out over here. Watch over here. All right. F. Too much time.
I was like.
Guys, let's scoot towards the back so we have a straight line. Hey, Brian, go that way. I'll leave Brian out. If two of you guys go with them, so kind of straight line in the back. We're all watching here to try and verify. All right, now we're gonna start a little bit faster. We're all keeping on so you guys can in the middle. If you see anyone do a hesitation, okay, well, here we go. Ready? S. P.
No.
You start off wrong. Here we go. Ready? P. S. D. F. S. P. All right. There's 4 now. Here we go. Here we go. Let's go. S. P. S. D. F. Oh, they're gone. There's 3.
Good up, sis.
There we go. Your comments here, though. I like it a lot. Here we go. P. S. All right, there's 2.
Ooh.
Here we go. P. P. I'll let it go. S. P. God. Congratulations. All right. Just so you know what your prize is, on your next quiz, you can get up to 3 incorrect answers automatically correct. Okay. Now, why was I sharing that with you? So you remember that whenever I say from here on out, hey, we're dealing with p orbitals, you never think, oh, 1 p orbital. You automatically think what? There's 3. Now remember this. The maximum number of electrons you can put in any one orbital are 2. Now, what I've done is this. You would normally think that if you're putting electrons in, you put them in the first energy level, then the second, and the third, and the fourth, and the fifth, and the sixth. Unfortunately, as always is the case, seemingly, we're going to have some electron or some orbitals that even though they're at a higher energy level, actually have less energy than a very complex orbital at a lower level. For example, if you take a look at this, do you see how if we're following the arrows, and this is how we actually fill orbitals. We go through the 1s, first. How many electrons can we put in there? 2. Then we go to the 2s. How many can we put in there? 2. Then we go to a set of 2p's, which is how many?
3.
But how many can we put all together in those? 6, right? Then where do we go? 3s, right? And we can put in 2. But we're following from the tail to the head, right? You guys have in your notes, I think, a similar line diagram. Yep, exactly the same thing. Although I filled it out a little bit more, which I would suggest doing as well. But after the 3s, don't we go 3p? How many are in a set of 3p? How many orbitals? In a set of p's, aren't there 3? So could we put 6 altogether in here? But then watch. Instead of going to 3D, we go to the 4s. What that must mean, therefore, is that the 4s orbital actually has less energy than a full set of complex 5D orbitals. This is important because the Aufbau principle says always put electrons in the lowest energy orbital. It doesn't say lowest energy level because that would mean we fill up the 3 before we fill up the 4. But because the arrow tells us this, we know that the 4s orbital actually has less energy than the set of 3Ds. Can you be okay with that? The best analogy I can give on this would be like 4th graders versus 3rd graders. As a whole, aren't 4th graders bigger, smarter, better looking, faster than 3rd graders? As a whole, right? But isn't it possible for the biggest, strongest, best looking of the 3rd graders to actually be bigger, stronger, faster than the weakest and most pathetic of the 4th graders? This is the same analogy. This 4s, if you're to characterize it as an orbital, it literally is like, I am a circle. I'm a sphere. And it's literally a very simplistic sphere. If you're looking at d orbitals, they are multi-lobed monstrosities, and there's 5 of them. These are more energy than the 4s, so we put them in the 4s before the 3D. Do you guys follow? So what I was just doing, if you have your notes in front of you, I would continue the lines down because I think in yours it kind of goes up to like 7D. It doesn't actually go all the way to the 7F. Part of the reason is that we never have need of using that many orbitals because there's a couple hundred orbitals that can be fit in, or a couple hundred electrons that can be fit in up to 7F, and the most we ever have in the periodic table is 110 or 113 or so. Are you with me so far? So what we're going to do right now is we're going to walk through how do we show people how many electrons there are in what orbitals, and we're going to start with different notations. And the first notation we're going to start with is something called orbital notation. And orbital notation is exactly what you think it might be. Orbital notation is where we actually write the entire, every single orbital and the electrons that exist in those orbitals. So I'm going to have, who's here, who's mathy, who can help me here with just basic calculus? All right, so we're going to play with 22 electrons. So our job is this. I'm giving you 22 electrons, and I want you to put them in their homes. Now, that is, your task is to put them in the lowest energy orbitals that are available based on that table, right? But let's just pretend that you're like, you know what? I'm having a terrible day. If I'm having a terrible day, my electron's having a terrible day. And so you take your electron, and you're like, boom, and you put in the 7F, right? Whereas they should be going first into the 1s, agree? How short-lived would your evil plan be? Because if I put an electron in the 7F, is this atom stable?
No.
No, isn't that electron in the excited state? And won't the atom want to rectify that by having the electron jump back down? Remember we said that electron can jump up and down in 100 millionth of a second? So that's about the amount of time that you would get to enjoy the cruelty that you imposed on the electron by putting it in a higher energy orbital, because wouldn't it just drop back down on its own? So the reality is, even as we're putting electrons into orbitals, they're going to set themselves up into the ground state on their own, as even if we are terrible at our job. Yeah? Kind of a safety net for us. So what we're going to talk about first is something called orbital notation. Orbital notation. And literally what we're going to do is we're going to take 22 electrons, and we're going to use the chart over here, and we're going to put those electrons into orbitals. So, and as we're going through this, is you're going to keep track of how many electrons we still have left to place. Okay? So, first of all, if I have my first electrons, what orbital are they going to go into based on the table? The 1s, right? Now, the way we do orbital notation is we actually draw the orbital as a line. We go 1s, and we put a line on top of it. And then we represent the electrons that we put in there as arrows. The first arrow in, we put as an up arrow. The second electron in, we put as a down arrow That's to represent the fact that the first electron in always spins in one direction, and the second electron in spins in the other direction. So their magnetic fields are opposite, so they don't collide with each other, et cetera, et cetera. But since we have to put 22, isn't it a safe bet to say that we're going to at least put 2 electrons in this first orbital? And I'm a big fan of the half arrow because it's super fun. So see how that is, instead of writing this, it can get kind of confusing. We write 1 half arrow up, 1 half arrow down, and that represents, this represents the first electron placed in the orbital. This represents the second electron placed in that orbital. Yeah. So we've placed 2 out of our 22. 20 left, right? We're going to go after the 1s if we follow the arrows. We're going to go to the 2s. Again, with orbital notation, we must draw the actual orbital. So we go 2s. How many electrons can I put in there? 2. So I'm going to go 1, 2. Now we hit the 2 p's. This is where our little game really has value. Because don't our 2 p orbitals, aren't they a set of 3 p orbitals at the second energy level? They're all named 2p because they're all p orbitals at the second energy level. But aren't there 3 of them? So wouldn't we have to go 2p, 2p, and 2p? Agreed? Can't they all together house 6? Now, in this case, it doesn't really matter the order in which we place those electrons into those orbitals. It really doesn't matter, simply because, don't we have how many left to place after those first 4? We still have 18 left to place, right? So if I have 18 left to place, I know these can each take 2. Would it make sense that I could just fill up all those orbitals? But let me remind you of a rule. And it's so important, it's called Hund's rule. And you have it in your notes, because just listen to see if it makes sense. Hund's rule says whenever you have a set of equal energy orbitals, you always put 1 electron in each one before you put 2 in any of them. Let me give you an example. Not that you need this, but let's pretend it's Christmas. And I don't know what your Christmas traditions are. We're still kind of figuring out ours with our family. When I was growing up, our Christmas tradition was as soon as it hit Christmas, aka 12:01, that's when we would open our presents. So it's kind of a cool thing. We would literally wait till 12:01, and then we would just open up all of our gifts, and then we'd like stay up for a couple hours, and we'd just sleep in the morning, have our whatever. We believe in Jesus Christ. Just kidding. Anyway, we still had Santa.
Would Santa come in the morning?
We never really worked through the intricacies of that because I think we pretty much debunked the Santa. For those who don't know, I'm not saying the Santa's not real. He could be real in your world. Anyway.
Wait, that's so sad.
Like, Santa was my childhood. We also had Halloween.
I feel like I was okay. I feel like I turned out okay. Now, I imagine this. Does any of you guys have 2 siblings exactly? So you're part of 3?
Yes.
Okay. So imagine that it's Christmas, right? And you come downstairs in the morning, or after Santa's come, and let's say your parental starts handing out gifts. That's how we kind of did it in our home. So sibling number 1, your parent gives them a gift and is all like, sibling, we love you so much. Here's a gift. All right. And sibling number 2, we love you so, so much. Here's a gift. And then they look you straight in the eye, they grab another gift, and they turn away from you and go back to sibling number 1 and go, you know what, we love you so much, we're going to give you a second gift. And sibling number 2, you are so special to us. Here's a second gift. Done with gifts. Now, if I know anything about teenagers, and I think I do, I'm guessing you're probably thinking to yourself, well, God bless them. Good for my siblings. They are truly 2 gifts each. Good for them. Good for them.
Okay, but actually, like, teenagers
Or, and I'm just speculating here, maybe it's an uncomfortable home environment after you've declared the unfairness of the whole thing. Problem? Now, that's how it is with orbitals. If you have 3 orbitals and you're like, 2 for you, 2 for you, 0 for you, this guy right here, not going to be happy. And hence, this set of orbitals, not going to be happy, and the entire atom is not going to be happy. Now, if it happens that you're like 1, 2, oh, we just ran out. Well, life is the way it is. Sometimes that happens. But come on, man. You're getting 2 each and I'm getting 0. There's going to be some carnage. Agree? I'm going to share with you an anecdote that you don't need, and I don't know if I like this on film, but we had an aunt that wasn't really an aunt. You probably other people. We call her our aunt because she gave us stuff, which we were really, now I'm looking at it, pretty horrible humans in that we would kind of prostitute ourselves for gifts from this aunt. Oh, Auntie Kaya, and so Auntie Kaya would give us tremendous gifts. So much so that my parents finally said, Kaya, enough. Like she was getting gifts that were just not way better than my parents' gifts to us. It was just not a good thing. So unbeknownst to us, which we would have put up a stern and a vigorous defense of Kaya's practices if we'd have been included in the decision-making process with our parents. But then they went ahead and said, you know what? No gifts for the kids this year. So Kaya, along comes Christmas, and I get a package from Kaya under the tree that is book-shaped, and shockingly, when I open it, it's a book. Yeah. Now, I'm going to say this, and this is part of me that I'm not proud of how I was as a human. Are you chewing gum?
Nope.
I don't feel like that's better.
Okay, she knew. She was like, because I saw you go.
That's just something I've always done. Just like I'm a very fidgety person.
All right.
Well, I was wondering if anyone else saw that.
I did not. I missed it, but now I'm enjoying it. I feel like I don't want to make that call down to the nurse. Child has swallowed a piece of plastic and it's lodged in the throat, but you feel like you're responsible enough to take care of it. And we're coming back. So I actually opened up the book and like trying to do like surreptitiously, like so I wouldn't draw attention to myself, and flip through the pages, like assuming that maybe a check would flutter out or something. And there was no fluttering of anything, right? So my sister, on the other hand, she gets her gift from Kaya, and it's a huge stocking, and it's jam full of stuff. I'm like, okay, that's odd. And so she starts pulling out things, and they are like incredibly nice gifts. Now, I don't know anything about makeuping, but she got like a full like makeup kit thing from a brand that I don't know. But it was like, I don't know, but it was like, evidently it was like $100 plus like gift. And she kept on pulling like item after item up. She got a camera. And this is like back in the olden days where the cameras existed before phones. And the camera she got was one that was like a digital camera. This is a long time ago. And it spoke. It was like, it is too dim. And so it would like adjust on its own. It was probably like a $200 or $300 camera, right? So every time that she pulled out a gift, my sister would look over at me and she'd be like, I keep on forgetting, Greg. What is it? Oh, you got a book. You got a book. Yeah. So it gets better. So we go through the entire thing, and the last item she pulls out of the stocking is a change purse. You know, like the for coins. But it's not filled with coins. It's filled with bills. And it's not filled with like $1 bills. It's filled with like 5, 10s, and 20s. And it's packed. And so this is like the ultimate like sister thing to do with her brother. She as she lays out all of her things in front of her, right? Commenting aloud how generous Kaya is. She like fishes into her change purse, pulls out a $10 bill, looks at me, throws the bill at me, goes, go buy another book. Boom. Yeah, true story. So I'm gonna share this with you. I was a teenager at the time. Oh, by the way, the book was really good, but that's really not the point. The book was the Dave Dravecki story. Now, there really is not. It's not. It's that my sister's terrible. Now, in fairness, I may not have always treated my sister well. And by the way, you'll appreciate the irony of how I look right now as a fat man. But all the way through college and whatever, I was an athlete and I was in extremely good shape. And there was a portion of time where my sister was a touch pudgy. And now that I have a daughter, I'm just horrified that I realize I'm going to stop the story. And I realize I'm also videoing it.
No,
So
start a story.
is that how it works?
No, because if you start telling someone something,
Yeah,
you
now we're
stop
on the edge.
halfway through.
Interesting. Anyway, okay, so I'll tell you, but you have to promise to not think badly. Like that's not promise you're not going to be able to keep.
Okay.
So there was a period of time where, when she was in her pudgy state, I may have not referred to her by name, but actually called her. You're gonna look at me differently. And again, there's part of you, and especially some of you, you're gonna look at me and go, "You got what you deserve, Dimitrich." I may have called her for a period of time, Fatty McPig. I know it was a lot, and I threw in Mick in there. Fatty McPig.
Wait, what was her name?
Diana.
Okay, and y'all know that thing from Diaper Movie Kid was like Patty. It's a fatty.
I-
Face just like a rabbit.
I will not say that may have impacted her negatively, but there was a period of time where she lost weight dramatically, and it was kind of scary, and I may have been a little bit to blame for that. We are good friends now. She's normal now. I mean, therapy gets through everything, really. Coming back to this. I used to use an example, and I probably should have, of like, if you're putting electrons in, you want to put one in at a time before you put two in any of them. We know there's going to be 6, so it really doesn't matter the order we put them in. I used to use an example of caves, and if 2 caves have a bear in them, then you go to the 3rd cave that's a non-bear cave, right? And then the other, and I was like, and what if you go and each of the caves has a bear in it? It doesn't really matter, but if one of the caves has 2 bears in it, you're probably better off going into one of the 1-bear caves, right?
Yes.
And then my students completely debunked that, because they're like, pretty sure 1 bear is good enough, and perhaps 2 bears will put you out of your misery quicker. So they kind of ruined my analogy. But however you want to think of it, Hund's rule says you put 1 electron in each orbital of equal energy before you put 2 in any of them. Can you give me a head bob if that makes sense? I apologize for the anecdotes. They really weren't necessary. But after we finish the 2p orbital, where do we go? Do we go to the 3s? And again, we must draw, and I really am hoping that you're drawing these along with me. We must put maximum 2 electrons in that orbital. Yeah? Counter girl, how many have we put in so far?
We're at 3S.
We can always count it this way, going 2, 4, 6, 8, 10, 12. We put 12 in, 1, 2. 10 left. After the 3s, where do we go now? The 3p. And we've got to include all of the 3p orbitals. 3p, 3p, 3p. And we know this just because we know that this can only hold 6 and we still have 10 electrons. Don't we know that all the orbitals are going to be filled? But just out of habit, I would really strongly encourage you to put 1 in each one before you put 2 in any of them. Right, Noah?
Yes.
How many do we have left to place here, Izzy?
4.
We have 4 left to place. Now, if you take a look on the little table, don't we go from 3p to then the 4s? So we're going to do that. And again, that's the out of order thing, right? We would normally think we go to the 3d, but the 4s actually happens to be less energy. So we put them in the 4s. And we put 2 in the 4s, leaving us with 2 left. Agree?
Yes.
And the only place left for them to go after the 4s, remember, we always follow from the tail of the arrow to the head, is to the 3d. How many are in a set of 3ds? 5. And here's the troubling thing that I never really liked very much about this, is that even if you don't use all of the 5 orbitals in a set, in orbital notation, you still have to include all of the orbitals. So even though we only have 2 electrons, right, we still have to include all 5 of the orbitals. So we're going to go like this. We're going to go 3D, 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 and 3D, and draw the spaces on top of them. There's still 2 electrons left to place, right?
Yeah.
So just to get it done with, we should put both those electrons in this first orbital, right?
No.
By the way, I don't know if you have multiple siblings, but how much worse would it be for the 2-gift child if all the other children got nothing? I'm feeling like there'd be some repercussions. In this case right here, we're just going to go, oh, sad day for you, but we just ran out, right? Now, this is what we call orbital notation, and in it, we can see where every single electron is placed in a particular atom. In fact, do you realize that we always put every electron in the same exact orbital, no matter what atom we have. For example, would you agree with me that the third electron in every atom will always go in the same place? Won't it always go, right, 1, 2, actually fourth. Let's say we do 4 electrons. Wouldn't the first 4 always go 1s with 2, 2s with 2? Yep. If I have 100 electrons, wouldn't it still have the first 4 be here? When I have 22 electrons, this is the configuration I have. But this is the same configuration. If I had 50 electrons that I needed to place, wouldn't the first 22 go here? Then 23, 24, 25, and move on. Agree? Now, this is 22 electrons. Right now, I want you to draw for me the orbital notation. You can continue on your own paper. I want you to do it for me for 35. Go. 35. Very quickly. Give me a wave as soon as you got it done. You can keep on going on this one. Just pretend now we're no longer at 22. We're going to 35. Is anyone here on NHS or something that helps with the recycling? Someone took my big box of recycling and I can't find it.
Sophomores can't be in NHS till.
Gotcha. That's something to look forward to.
I was thinking about vocab.
I'm not gonna lie, I'm fairly impressed by you there, Noah. That was a calculated guess. Okay. Anyone gotten it done yet? All right. We're just gonna change this with the magic of an eraser to 35 electrons. And when we do that, we know that we placed 22 right here, right? But then couldn't we add on an additional 13 to get to it? So could we go like this? Notice how, even though I know I'm going to fill this, do you see how I put 1 in each one before I put a second one in any of them? And then after I finish the 3D, where do I go? 4P, right? And the 4P, don't they come in sets of 3? And again, as silly as our little game was, the reason I emphasized that I wanted you to go 1, 3, 5, 7 for these is to automatically know how many in a set you have to draw for each orbital. In the 4P, don't we have to put only 5 electrons in there? Right? So if we're putting 5 electrons in, wouldn't we go like this? 1, 2, 3, 4, 5. Now, what's important about this is, see this electron right here? Isn't that the last electron that we place? If you didn't understand how we filled it, mightn't you think that this is the last electron we placed? But it's not. Isn't it 1, 2, 3, 4, 5? That's something we're going to come back to in a little bit. So that was super fun doing 35 electrons, right? Orbital notation. Now I want you to do 87.
No.
We just do 87.
Okay, so the correct response should be, come on, man. And so I'm not going to make you do 87. What I'm going to do right now is I'm going to show you 2 shorter ways to do the same thing. Okay, so this right here, if I ever ask you in the future to do orbital notation, it's going to look like this. Every single orbital with the electrons being represented by arrows. This is called orbital notation. Yes?
Are we going to have like the chart? Like
no, but you're going to have something better than that. Yep. So those of you guys that did what all of you guys did when you guys did the hotel thing, what we're going to do right now is instead of drawing out all the electrons, we're going to write the number of electrons in a set of orbitals as a superscript, kind of like an exponent, but in a superscript, right? So what we're going to do right now is we're going to do the same 35, but this time we're going to do it, we call it electron configuration. So it's electron configuration notation. We're going to do the same exact 35. Now, because I know that I did the order correctly here, I don't have to go back to the table here to show me where I need to go. So let's just write them out. Let's start over here with the 1s. So in the 1s, how many electrons have I placed in there? 2. So wouldn't we just go 1s2? By the way, the more I think about it, that POGL activity you guys did was pretty solid, wasn't it? Yeah. The kind of understanding how electrons are placed, I like it very much. How about the 2s? Wouldn't it also have 2? But now watch. In the 2p, how many do I have altogether? 6. So I'm going to go 2p 6. Now, do you understand that in this case right here, it's accounting for all the orbitals together as one set, and we put the electrons in right here. So it becomes 2p6, then what? 3s, 2, 3p, 6, 4s, 2, 3d, 10, and then finally 4p, 5. I'm glad they said 5. Why isn't it 6? Yeah, it's not how many they can have, it's how many they actually have. And aren't there only 5 electrons in there? Now, I'm going to go ahead and guess that when you look at this right here, you're going to say to yourself, self, that's shorter. Agreed? But even that being short, not very many of you are going to want to do like 120 or 100. Actually, that doesn't exist. But none of you don't want to do like 118, which is so close to 120, right? No one wants to do it this way. So I'm going to teach you right now something called shorthand notation. And what's cool about shorthand notation is that you can do shorthand notation in combination with orbitals, or you can do shorthand notation in combination with electron configurations. And here's what we do. We literally take the noble gases and we use the noble gases configurations to replace portions of our configurations. What am I talking about here? Well, are you guys all okay with the idea that the noble gases are the far right-hand side of the periodic table? Helium is included up here because it has 2 electrons in its first energy level, and isn't that a full energy level? That's why it's included there, but we don't really consider it to be one of the noble gases, and we definitely don't use it for shortcuts. So first one here, isn't it neon? So all I want to do is I want to draw out neon, what its electron configuration would be. So if I look at neon, wouldn't neon be 10 electrons? And if I'm putting in 10 electrons, wouldn't that look a little like this? Wouldn't it be 1s2, 2s2, 2p6? Agree? Yeah. So what we can do now is this. Neon can replace everything up to 2p6. So instead of writing this, I could instead write neon, and it would replace that. Now, we can only do this with the noble gases. You can't just randomly pick one. But let's go to argon. By the way, you're going to see a pattern really quickly. See how neon's in the second row and it ends in 2p6? Okay. Argon, which has 18 electrons. We're going to do the same thing with argon. And if we wrote out argon all the way, it'd be 1s2, 2s2, 2p6, 3s2. And those of you that guessed out loud, you were right. You see how it ends in 3p6? Yeah. So instead of writing 1s2, 2s2, 2p6, 3, instead of writing all of this, we can instead just write argon. So couldn't that replace everything up to here if I wanted to? Now, you guys have already cracked the code. But this is kind of cool. If you know what row your noble gas is on, not hard to see there. If you know what row your noble gas is on, you know that that row is going to end in P6. So 2p6, 3p6, 4p6, 5p6, and 6p6. So after argon, isn't there krypton? And krypton would replace everything up to 4p6. And then we have xenon, and it would replace everything up to 5p6. And then finally we have radon, and it would replace everything up to 6p6. Now we have tools that can make our writing of longer configurations much, much easier. Are you with me? Let me give you an example. Let's pretend that I wanted you guys to do the shorthand configuration for aluminum. Now, everyone right now, I want you to put your finger on aluminum on your periodic table. Really, really important. Okay, so whenever we're doing electron configurations and we're doing the shorthand, you will take whatever, can I start that sentence again, please? You'll put your finger on the thing you're trying to write, and you go backwards to the nearest noble gas you pass. It's kind of like pass and go, right? The nearest, in Monopoly, by the way, the nearest one you've passed, you're going to write that down. So what's the nearest noble gas that we've already passed when we want to write out aluminum? So we're trying to do aluminum, and the nearest one we pass, isn't it what? It's neon.
Why is neon?
Now, really quick, would you acknowledge two things about neon? First, doesn't neon have 10 electrons? And second, Doesn't neon replace everything up to 2p6? So here's all we have to do. We just have to know how many electrons more we have to put in past 2p6. How many electrons does aluminum have? 13 electrons, right? So wouldn't we have to just add 3 more electrons to this to make the configuration right? So what we're going to do is this. Since we know neon goes up to 2p6, don't we go to the next thing past 2p6? And what's that going to be? Wouldn't it be 3s2? So we're just going to go neon, and then we're going to go 3s2. But then we want to put in 2 electrons of the 3 that we need. And after the 3s2, where are we going to go? 3p1. And that is short. Any questions for me? Let's try one that's a little bit more intense. Yes?
On the pocket video examples of some, it says like iron is 26 electrons and you can use that, but you said it's just 3 times.
So I don't know what's in the note packet, but I may be misunderstanding what I'm saying with that. You can only use the noble gases to replace portions as a shorthand. Only ever. So let's do this one. Let's do silver. Ag. I want you to try it on your own. Let's do Ag on your own. And you're going to have to do the mathematics, and then you're going to help me with it. So we're going to try and do Ag, and we want to know what its configuration is. Give you a moment here to just think it through. I've grown tired. So isn't the first thing that we do, isn't the very first thing that we're going to do, isn't it going to be to figure out which noble gas we've passed? So when I put my finger on silver and just backtrack literally to the nearest noble gas we passed, isn't it krypton? Now, off the top of my head, doesn't silver have 47 electrons? And doesn't krypton have 36? So I know that once I have krypton's configuration, won't I still have to put in 11 more electrons? So what I'm going to do then is I'm going to go over here and I'm going to write it down just so I know. Doesn't silver have 47? And if I use, didn't we say we have to use krypton? Yeah. Krypton has 36. So in my mind, I know I have to add in 11 more electrons to this. Agree? But I also know based on the row that krypton is in, isn't it in the 1, 2, 3, 4th row? Want to replace everything up to what? 4p6. So on my diagram here, it's going to replace up to 4p6. So after 4p6, I still have to put in 11 electrons. So where am I going to go after 4p6? 5s. I'm going to go 5s2, right? Now I have 9 left to place. After 5s2, where do I go? 4d. Now, here's the thing. I only have 9 more electrons to place, right? So I'm just going to write 4d9. Not 4d10 because we didn't fill it up, agree? It's 4d9. That's my shorthand.
Question. But how can we memorize, like, what is the order for the arrows to go down with that?
You'll have this table until I provide you with a better way of doing it.
Okay.
So right now, this table is your go-to. You're going to have it with you, and you're going to use it to do all these types of problems. Yes, but no. I'm going, so this right here, this is a method. I'm teaching you a method of using the lines. That's how I learned it first as well. But in a couple of class periods, I'm going to show you how to use the periodic table to do all of this. And you're never going to even think in the future, oh, do I have to worry about the arrows? Because the periodic table literally will line up everything for you. Like right now, doesn't the periodic table already kind of help us use shorthand? It gets even better because different parts of the periodic table match up with different energy levels and different orbitals, and it's going to become a lot easier for you. So short answer is no. But the way I did this table, like in case you wanted to memorize it on your own, I literally went like this. I wrote down 1 through 7 and put an S in the first column. Then I went 2 through 7, wrote a P. 3 through 7, wrote a D. 4 through 7, wrote an F. And then literally I just made lines through. It took me 30 seconds to a minute to do it. You in a pinch, if you had to, you could do that. But I'm telling you in advance, you're not going to have to do that. Okay, now, do you understand that I could do this exact same thing? And let's say I'd asked you to do it instead of shorthand electron configuration. What if I said shorthand orbital notation? Well, help me out, dear students. What's the difference between orbital notation and electron configuration? One, you have to put every single orbital and, as Ryan said, the arrows, right? Electron configuration is nice, so we just kind of synopsize it together. But let's say I want to do this same thing, but I want to do it in orbital notation. Watch what I do. I'm not going to recreate the wheel because don't I know that this has to be the configuration, but now it has to be drawn out? So couldn't I go like this and go krypton? But then wouldn't I have to go for 5s when I go 5s and 2 arrows? And this is where it becomes truly painful. Instead of being able to just go 4d9, aren't there 5d orbitals? Remember the game we played that was super great now that we were thinking about it? We wouldn't have to actually write out all of the 4d orbitals. Now, in this case, we're putting 9 electrons in here. How do we place electrons in orbitals of the equal energy? 1 before we go back and put 2 in any of them. That's going to matter to us a little bit later on. So for those you're like, I do what I want. And you're like 2, 2, 2, 2, 2, 1. It's going to give the appearance that this 1 is your last electron, but it's not, because when we put them in there, it actually goes like this: 1, 2, 3, 4, 5. This is the 5th electron placed. 6, 7, 8. No, that's a terrible arrow. Isn't this right here the last electron that's actually placed?
Yeah.
Again, for right now, it doesn't matter that much to you, but this method actually will help us with that. So hopefully you're getting a glimpse of the fact that you can actually do these problems using the periodic table and make it a lot more straightforward for yourselves. You absolutely will. And on top of getting the periodic table, I'll give you a blank one that you can, at the very beginning, you can write on it however you want. So you can set up the periodic table to help you with the notations. In a bit, you're going to look at the periodic table and you're going to think to yourself, okay, they came up with this periodic table a couple hundred years ago, before they understood anything about orbitals and energy levels, and it fits our system here perfectly. It's unbelievable. If you ever wanted, hey, do I believe in God or not? The order behind this and how it could fit perfectly, by chance, it just doesn't happen. Now, any questions on what I've just shared with you so far? These are the 3 main notations. Now, there is a 4th notation that we use, and it is called the electron dot notation. And literally, it is the simplest notation ever. Let me show you this really quickly so you have it. Ready? So the electron dot notation tells us how many valence electrons or outer shell electrons every atom has. Do you realize that there's different energy levels, right? The outermost energy level in an atom, we call that the valence energy level, right? And those electrons, those want to meet and greet other electrons in other atoms. So here's what we know. Group 1 all has 1 valence electron. Group 2, 2 valence electrons. Skip the whole middle. 3, 4, 5, 6, 7, 8. Now, how do we do electron dot notations? Well, let me show you. Let's say I asked you to give me the electron dot notation for nitrogen, right? Take a look at nitrogen. Isn't it in group 1, 2, 3, 4, 5? That means that nitrogen is going to need 5 dots around it. So what we do is we write the symbol for nitrogen, and then we pretend it's like a box. And the maximum number of dots you can put on either side of a box is 2. So couldn't I go like this and go 1, 2, 3, 4, and the 5th one you can put whatever you want, 5. Yeah?
What's this called?
Electron dot notation. You cannot do this. 1, 2, 3, 4, 5. Like I'll have it in picnic over on this side. Typically what we do, and you can do it more than one way, I like doing it like 2 on a side until I run out. So like this, you can write it like this, or you can do it like this. Yeah, that's how I kind of prefer it, but it doesn't really matter. What if I did oxygen? Doesn't it have 6? So with oxygen, can I go like this? If you're like a rebel and like, I do what I want, and you're like, random. That's okay. But you cannot be like kind of like looking back, like knowing that you've done something wrong. Like, you just can't do that. And I'm saying this, and you're like, okay, that's silly. No one's going to do that. Every year I have a student on the test that is like, I put them all here. And I'm like, why? Why would you do that? 2 maximal on the side, pretend you have a square on the outside. That's electron dot notation. You're going to notice in the homework that asks you for that. That's literally probably the easiest thing, because if you can count, you're okay. Now, where it becomes hard is what if you get one of the ones that's in the middle block? Agree? For right now, if you get ones in the middle block, I want you to do nothing. I will show you what to do with them in the future, because we really don't care about the electrons that are outer shell electrons in the middle for one huge reason, which I do not have the tools yet to explain to you. Is that okay?
Yeah.
So right now, your homework is going to be this worksheet I'm going to hand out to you, which is essentially doing electron configurations. Now, on the worksheet itself, it tells you to do quantum numbers. Now, did I teach you today about quantum numbers? Do you know anything about quantum numbers? Probably not. So that part of the assignment you're not going to do yet, but don't, in your fervor to make sure you don't do it, scribble it all out, because we're going to come back to this, and I'm going to show you how to use these things here to figure out the quantum numbers. Fair?
Yeah.
All right.
So where's
That's the end of the lecture.
On the portal,